So I talked about how we have the free energy in the universe. Let's talk about one of the components of free energy, which is the enthalpy. Now, enthalpy is represented by the letter H. And what enthalpy represents is the sensible heat stored within a system. So basically, when we change enthalpy, we're changing heat and therefore changing temperature of the environment. Now, there are two conditions for the change in enthalpy. The first is when we have a delta H less than 0. Specifically, our final enthalpy is less than our initial enthalpy. We define these as exothermic reactions. And exothermic reactions are ones where the heat is released into the environment, so we see a positive change in the temperature of the environment. Second condition we can have is delta H greater than 0. And for these types of systems, we finish with more energy than what we started. And so we call these endothermic reactions. Now, for an endothermic reaction, what ends up happening is the temperature of the environment will go down. All that heat being pulled into the system is being pulled out of the environment, lowering the temperature. Now, preferably to make a reaction favorable, we like to have the reaction exothermic because we're losing heat energy, and that's where we want to go with making a reaction favorable, is losing energy. There are plenty of examples where the delta H is greater than 0. Specifically, if you look at cold packs. Break a cold pack, it gets cold, that's a chemical reaction. Now, enthalpy actually is composed of two terms. For those of you in the 151 level, you can skip over this. For those of you in the 152 level, just take a quick look. So when we say delta H, we're actually saying there's two changes. First is delta U. And delta U represents the energy of bonding. Specifically, it's describing the internal energy within the molecule. So this is due to the vibrations, rotations, translations, and all that energy wrapped up in those bonds. We also have the delta PV terms, and this is called the work term. Now, this is going to describe the energy due to the fact that the molecule exerts a pressure against the environment exerts a pressure against it, and the molecule has a defined volume. This delta PV is the work that the molecule can do like a piston. So if it expands, it does work against the environment. If it's compressed, the environment does work against it. And this is going to be what wraps up into our delta H term. Now, delta H, a couple of other important points. First of all, typically we measure this in units of kilojoules per mole. So these are fairly large amounts of energy wrapped up in delta H's. The second is that if you're looking for a good range, typically delta H is somewhere between plus or minus 25 and 500 kilojoules per mole. It can go as high as 1,000 kilojoules per mole. That's not unreasonable. Typically, those are high energy combustion reactions, though, something like octane burning and oxygen. That'll definitely get you something like 800 kilojoules per mole. But a reasonable answer for something like delta H, 25 to 500 plus or minus, depending on whether or not you work with an endothermic or exothermic reaction.